Okay, so we're in section 4.4 now, dealing with linear independence. And to motivate the discussion of linear independence, I'm going to go back to what we talked about in 4.3, where we discussed spanning sets. The idea there was that given some vector space, V, and some finite set of vectors within V, we're asking the question of whether or not that set spans all of the vector space V. And what that means is that set of vectors, that small set of vectors, sufficient enough to account for all of the vectors in V if we look at all of the linear combinations of those vectors. We looked at some examples there of sets that were spanning sets, not spanning sets, and some theorems in that regard. One thing we didn't really address, though, in that section, which is going to come up here, is the question of uniqueness. So just because we have a spanning set for a vector space, which means every vector in that vector space can be written as a linear combination of the vectors in that set, does that mean that every vector in the vector space has a unique representation as a linear combination of those vectors, or can a vector in that vector space have several linear combinations of the vectors in whatever set we're talking about, depending on how we choose those scalars? It's a little bit vague, but let's use an example to sort of illustrate this. Think about R2 for a moment. And specifically, let's look at the vector 1, 2 in the space R2. And let's consider the set S, which has these three vectors in it. Notice the first two vectors are your standard basis vectors, I and j, but written in component form 1, 0, 0, 1. And then we're going to include a third vector in there, 1, 1. Okay? Down here, I have two different linear combinations, and by different I mean with different choices of scalars, but they both come out to the vector 1, 2. And notice they're linear combinations of these three vectors here in S. So what this is showing is that for this particular set, S, linear combinations of at least some of the vectors are not unique. I can find different sets of scalars to multiply these vectors by in my linear combination to still arrive at the same vector. Now, that's not a very desirable property. We would prefer it if the set S allowed for one and only one linear combination to represent each vector in R2. And the goal there is that it leads to a concept of coordinates, which we'll talk about in more depth in section 4.5. What the question of this section is, what property needs to be in place for a set like this so that we get uniqueness when we talk about these linear combinations as representations for vectors in whatever vector space we're looking at. And that condition turns out to be this thing called linear independence. So what is linear independence? Well, suppose we're working in some vector space V, and we're talking about a set of vectors from V. I'm going to call the set S, and in this case, let's say that the individual vectors are V1 through Vn. Now, if the following equation is true, so this is, notice I'm forming a linear combination of these n vectors, where the scalars are k1 through kn, and I'm setting it specifically equal to the 0 vector here. If this equation is only ever true when all of the scalars are equal to 0, then we call that set linearly independent. Okay? And clearly, if I multiply each vector by 0 and add them all up, I would get the 0 vector. The question of linear independence is that the only way that we can get the 0 vector by forming a linear combination of this type. If the equation is true for any other set of scalars, k1 through kn, anything other than what I would call the trivial solution, all zeros, then we call that set linearly dependent. So let's start with an example. And this is the same set of vectors that we looked at up here. Remember, this set of vectors didn't give us the uniqueness that we wanted for these linear combination representations of vectors. And the reason for that is because this set is linearly dependent. But to show that, what we need to do is create create a linear combination of these three vectors that is equal to the 0 vector, but the constants or the scalars are not necessarily all 0. In this one, I notice that if I do 1 times 1, 0, plus 1 times 0, 1, minus 1 times 1, 1, then these two are going to add up to 1, 1, and this will become negative 1, negative 1, adds up to the 0 vector for R2, which is 0, 0. Notice the scalars were not all zeros. In this case, none of them were zeros, but in order to have linear dependence, all you need is to have at least one of them not being a 0, and that gives you linear dependence. So this set is linearly dependent. Now the tricky thing with this one, I came up with these scalars just by thinking about the set and kind of trying something and making it come out to 0. In other cases, especially if the sets are larger or if the vectors are more complicated looking, it's not necessarily that easy to just come up with scalars to do this. So we need a more deductive approach, a more direct approach that doesn't require a bunch of guesswork, and we'll see that in later examples. Now, if I were to take this vector 1, 1 and throw it out, just get rid of it from this set, getting me down to just this set, 1, 0, and 0, 1. Or in other words, the set of standard basis vectors for R2, this one turns out to be linearly independent. Now, how do we show that? Well, again, what I want to do is form a linear combination of these two vectors, but I'm not going to make any guesses as to what the k's could be. So k times 1, 0 plus k1 times 1, 0, k2 times 0, 1, and I want to set that equal to the 0 vector for R2, which is 0, 0. Okay, now the goal here is to show that if this equation is to hold, then k1 and k2 have to be 0 and they can't be anything else. So what we do is we multiply through and we make a system of equations. k1 times 1 plus k2 times 0 equals 0 is the same thing as saying k1 equals 0. That's what that simplifies to. Similarly, k1 times 0 plus k2 times 1, setting that equal to this second 0, would say that k2 is equal to 0. Solving it shows that those two scalars have to both be 0, and that by definition gives us linear independence. What does that mean? Well, again, if this linear independence condition gives us uniqueness, then what that means is if I take any vector in R2 and represent it as a linear combination of these standard basis vectors, that linear combination is the only one that would work for whatever vector we're doing that with. Okay, so let's go ahead and move on. Here's another example, just to start looking at this with a different vector space. So we're going to work in P2 in this one. I have 4 polynomials in this set, and they look like 1 plus x, 1 minus x, 2x squared minus 4x plus 1. Those 4 polynomials, I'm trying to determine if they form a linearly dependent or linearly independent set. So this one, I'm going to have a lot harder of a time trying to guess constants if this turns out to be linearly dependent, or guess scalars for that matter, like I did in our first example. So I'm not going to try and guess scalars that would make this equal to 0. I'm just going to make a general linear combination, k1 times 1 plus x plus k2 times 1 minus x plus k3 times 2x squared plus k4 times x squared minus 4x plus 1 equals, now remember the 0 vector in P2, or Pn for any n, is the constant function 0. But what that means is if I were to write this in the form of a polynomial in P2, it would look like 0x squared plus 0x plus 0. So my constant, my linear term, and my quadratic term all have coefficients of 0. That's important because that's how I'm going to come up with a system of equations to work with. Notice if I were to try and simplify this side, multiply k1 times 1, which is k1, plus k2 times 1, which is k2. This k3 isn't being multiplied to any constant here. And then k4 times 1, that would be plus k4. And I want that to equal 0, because 0 is the constant term over here. And then if I do the same thing for my linear terms, k1 times x, coefficient there is just k1. k2 times negative x, the coefficient would be negative k2. There's no x term here. K4 times negative 4x would be negative 4k4, and that should come out to 0 as well. Okay, and then moving on to the quadratic term. If I multiply, well, if I look at these first two terms, there's no x squareds in there, so that's not going to contribute anything. I'm going to have a 2k3 as the coefficient on this x squared term plus a k4 on that one, and that's equal to 0. Okay, now notice what we have is a homogeneous linear system because of the zeros here. So I'm going to turn this into an augmented matrix. 1, 1, 0, 1, zeros all down here. 1, negative 1, 0, negative 4, 0, 0, 2, 1. Okay, now what is the question that we're trying to answer here? Is the original set of vectors, original set of polynomials, linearly dependent or linearly independent? And remember that concerns these scalars. So k1, k2, k3, k4, do they all have to be 0 in order for this equation to be true? Or could they also equal some other set of numbers, not all of which are 0, that still gives me a 0 here? And notice the k's are the unknowns in this system of equations. So turning that into a question, or framing that in the language of linear systems of linear equations, we're basically trying to determine if this homogeneous linear system has only the trivial solution, which would give us linear independence, or if it has non-trivial solutions, that would give us linear dependence. So normally we would approach this by doing Gauss-Jordan and solving, but remember we have some results with homogeneous linear systems that allow us to arrive at an answer without doing anything else to this. Remember, homogeneous linear systems only have two different cases. They never have no solutions at all. They always have at least the trivial solution, and then if they have more than that, then they have infinitely many solutions. What gives a linear system infinitely many solutions? The presence of at least one free variable. How can we know if there's going to be a free variable? All the way back in section 1.2, we talked about, I think it was 1.2, we talked about a theorem that I believe it was called the free variable theorem that discussed this. You compare the number of equations to the number of unknowns here. I only have 3 equations, but I have 4 unknowns. The fact that there's only 3 equations here means there's only room for at most 3 leading variables. Notice if I did Gauss-Jordan on this, my diagonal of leading ones would stop here, and then I'd have this extra column here that doesn't have any leading ones in it. Or, you know, it's possible that I have a leading one down here, but I had to jump over one of these columns or something like that. The point is, I have more unknowns than I do equations. And in the case of homogeneous linear systems, this guarantees at least one free variable. That means this will have infinitely many solutions, which means there are non-trivial solutions, which means this set is linearly dependent. So linearly dependent. Okay. Now I'm talking through that reasoning without writing down everything I'm saying. If this were on a test, you would have to show me more than this. You would have to explain how you get from here to here, and that would involve writing some of the things that I just said. Or you could do Gauss-Jordan to, you know, show that this actually does have a free variable. All right, let's look at another example. This time we're working in the set M2 or M22, the vector space M22, sorry. And I have this set of 3 matrices, and same question, is this set linearly dependent or linearly independent? So we approach it the same way. Create a linear combination out of them. K1, 1, 1, 0, 0, plus K2, 0, 0, 1, 1, plus k3 times 0, 0, 1, 1. And remember, we always set it equal to the 0 vector for that vector space, which in this case looks like a 2 by 2 0 matrix. Okay? Now think about the linear system that comes out of this. I have 4 entries in each matrix. If I multiply the k1 into this one, k2 into this one, k3 into this one, and add the 1, 1 entry from each matrix, I can set that equal to 0. That's going to be k1. This is a 0 here. This is a 0 here. So k1 equals 0. Okay? Now my 1, 2 entry is going to look like k1 plus k2 plus a 0, so that's going to be a 0. Okay? Then my 2, 1 entry, 0, 0, k3. So I have k3 equals 0. And then my fourth equation, I'm going to have 0 plus k2 plus k3 equals 0. Okay? Now for this one, I'm not even going to waste my time with an augmented matrix, because again, the goal is to just determine whether there's non-trivial solutions to this or not. But notice that this system of equations came out really, really nicely. 2 of my variables, 2 of my unknowns are already solved for. k1 is equal to 0 and k3 is equal to 0. The only question now is k2. But whether I look at this equation or this equation, since those are the only 2 that have a k2 in them, I can substitute either k3 equals 0 here or k1 equals 0 here, and in either case we get k2 equals 0. So I have k1 equals k2 equals k3, which equals 0, so I have linear independence now. Let me say linearly independent. Okay. Generally, when we're looking at sets like this, again, we want linear independence. That's the desirable property for a set like this. Okay, not saying linear dependence is bad, but it's not going to serve the purpose that we want these sets to serve. So let's look over a couple of theorems here. This is the theorem that I sort of used to motivate this section. And we've been saying that if a set has linear independence, then that implies this uniqueness property of representing vectors as linear combinations of vectors in this set. We never proved that. I've just been saying that's true. So this is the theorem that establishes that. Let's suppose we have some non-empty set S, and it contains these vectors from a vector space V, V1 through Vn. Then this set of vectors is linearly independent if and only if every vector in the span of those, and remember the span of any set of vectors is a subspace of V. So it's linearly independent if and only if every vector in its span can be represented in exactly one way as a linear combination of these vectors, these V's here. It's an if and only if theorem, so I have to prove both directions. Let's begin with this one. Suppose that the set S described up here is linearly independent. What we need to show now is that uniqueness property. So what we do is we let V be any vector in the span of those n vectors, V1 through Vn. And the fact that V is in the span means we can represent it as a linear combination of the vectors in S. So let's actually give it 2 representations. Now this is a standard way of proving a theorem that suggests uniqueness for something. We assume that 2 of that thing exist, and then use whatever assumptions are being made in the statement of the theorem to prove that these are in fact the same. That means that there's really only one linear combination that gives us V in this case. So I'm going to call these 2 linear combinations, or I'm going to use C's for this one and K's for this one. If I want to show that this linear combination representation for V is unique, then I need to show that each of these scalars, each of these corresponding scalars between the 2 linear combinations are in fact equal to each other. That is, I need to show that C1 and K1 are equal, C2 and K2 are equal, and so on. So how do we do that? Well, because both of these linear combinations are equal to the same vector V, then that means they're both equal to each other. So I can set this one equal to that one. And then if I combine like terms by subtracting all of these k terms over to the left side, notice I get this new linear combination, c1 minus k1 times v1, plus c2 minus k2 times v2, and so on. And all that would be left on the right-hand side is the zero vector, since I subtracted everything away. However, by the assumption that we made at the beginning of this proof, the set of vectors v1 through vn is linearly independent. Remember, that means that if a linear combination of those vectors is equal to 0, then all of the scalars, all of the coefficients in that linear combination have to independently be equal to 0 as well. So in other words, c1 minus k1 is equal to 0, c2 minus k2 is equal to 0, cn minus kn is equal to 0. All of those are equal to 0. Solving each one of those for the c gives us c1 equals k1, c2 equals k2, and so on. That's what we wanted to show. Because the scalars are all, corresponding scalars are all equal, these two linear combinations are in fact the same linear combination. And so this linear combination representation of v is unique. Okay? Let's go the other direction. Let's suppose that every vector in the span of v1 through vn can be expressed in exactly one way as a linear combination of the vectors in S. If a vector is in this subspace of v, then by definition it has to be representable by a linear combination of these vectors. But our assumption here is that there's only one way to do that now. The goal is to prove that the set v1 through vn is linearly independent now. So if that's true, then let's specifically look at the linear combination of vectors as equal to the zero vector. We know that this is a subspace, so it contains the zero vector. So we have k1 through k1 v1 plus k2 v2, etc. equals 0. We know that one solution to this has to be k1 equals k2 equals all the way through to 0. Each of these scalars would equal 0. That's one way to create this linear combination. But the assumption that we made at the beginning is that for every vector in this span, there's exactly one way. So if we've found one way to make this linear combination equal 0, by assumption it must be the only way. So that means k1 through kn are all equal to 0, and that gives us linear independence. Okay? This next theorem, we'll end this video with this one. This one will go pretty quick. A couple of useful properties of linear dependence or linear independence. So first of all, a set with finitely many vectors that contains the zero vector is linearly dependent. In other words, no linearly independent set can contain the zero vector. If you notice, none of the examples we looked at previously where we had a linearly independent set had the zero vector in it. That's because it would automatically make it linearly dependent. That one's very easy to prove, and your book proves that. So I'm not going to do that one. I'll let you look at that one up in your book. I'll do the proof for part B. This one says that a set containing exactly two vectors is linearly independent if and only if neither vector is a scalar multiple of the other. Okay, this one's also not that hard to prove. It is stated as an if and only if proof, but because the proof itself is not super difficult, I'm going to do one direction and leave the other one as an exercise that you can do optionally. It's good practice to see if you can come up with that proof on your own. So we're going to prove this direction. We're going to suppose that we have a set of two vectors from some vector space. I'm going to call it v1 and v2, and we're going to suppose that it's linearly independent. Okay, what I need to show is this second part of that statement. Neither vector is a scalar multiple of the other. So the way I'm going to do that is assume the negation or the opposite of what it is I'm trying to prove. I'm going to assume that one of the vectors, let's say v1, is actually equal to a scalar multiple of the other, k, some scalar, times v2. And I want to show that this leads to a contradiction. Okay. Now, first of all, neither of these vectors can be the zero vector, because by part A, if either one of them were the zero vector, then the set would have been linearly dependent, which is different from what we assumed here. So neither of these are 0. And notice that also implies that our scalar k can't be 0 either. Because if it were, then v1 would equal 0. So this has to be some non-zero scalar. So that's what we're saying here. Now, what would happen if I formed this linear combination? Actually, let me rephrase that. Let's take this identity here, or this equation relating v1 to v2, subtract the k v2 from both sides, giving me this linear combination. v1 plus negative k v2 would equal the 0 vector because I subtracted it over. This is a linear combination of the two vectors v1 and v2, where at least, actually both of the coefficients on these two vectors are non-zero. We made an argument for why this is non-zero, and this clearly is a 1 here. Okay, so the fact that even just one of those scalars is non-zero means that we don't actually have linear independence. That's a contradiction because we assumed linear independence. So that contradiction means that this additional assumption here, that v1 and v2 are scalar multiples of each other, must be false. That proves the part B of this theorem. Okay, we'll pick this up where we left off in the next video.